So thanks a lot for the organizers for the kind invitation. So I'm Benoit from Grenoble. It's in the same time zone as in Rwanda, but unfortunately I couldn't come. And I'm happy to give this presentation. So the goal of this presentation is to give a brief overview of the topic of my research. The title is Understanding the Role of Entanglement in Quantum Computing. So I tried to find a fancy title, but of course, in the next 30 minutes, I will not cover completely the topic in all details. I will just give a brief introduction to what I do, what I try to do in this context. And so first, I will describe the concept of entanglement in the context of quantum computing. So how can I define it? How can I quantify? And why it is important to try to measure this in this quantum device. And second part will be about a method which indeed allows to measure entanglement in such experiments. So I will present the framework, basic idea, intuition, and give a few illustration of now how it is implemented in some quantum computers. So starting point for me is we know that quantum computers do exist. I guess you have seen many examples in the last days. I guess you also know that they are not yet completely useful or as useful as we would like them to be. And the reason is that these devices suffer from errors. Okay. So here I show you an illustration. It's a plot from the Google team in their supremacy experiment, where they measured actually the fidelity of the device as a function of number of qubits. So we have order 50 qubits. Typically, the fidelity decays as a function of the number of qubits to reach 10 to the minus 2 or something like that for the current system sizes. And it's a bit sad, but it's also an exciting time for us because we have this experiment and we are trying to understand a many-body quantum state which is there and which suffers from decoherence. And we are not able to use them already to factorize number or to run Grover's algorithm, but we can use them to understand the physics. Okay? And then we can try to improve them, of course. So, in my opinion, right now, quantum computers are very useful for benchmarks. So we need to understand what's going on there. And the second aspect is you can also use this device to do quantum simulation. So you can try to understand the physics of a many-body quantum system under time evolution. And I will be more specific in a minute about that. So when you're trying to understand quantum computers, errors, or how they behave, I would like to convey a message that you can look at one concept, which is entanglement. Entanglement can be used as a resource, so it's typically useful for algorithm, and is also very fragile. So if you're able to measure a large amount of entanglement, would be a good sign for your quantum computer. And entanglement is also important to understand the physics behind these devices. I will explain this in a minute. So what is entanglement? So I will give the first definition is, suppose your quantum computer is made of qubits. You can define bipartition. So you can divide your system into two parts, A and B. So here you have 4 qubits in A, 4 qubits in B. And the definition of entanglement is that A and B are entangled if and only if you cannot write the wave function of a system as psi A times psi B. Okay. This you I guess you already know. And one example of entangled states is, of course, the famous Bell states for 2 qubits. I write 0, 0 plus 1, 1. I cannot write this as a simple product. So why this simple concept, which I can define for 2 qubits, but also for n qubits, so for quantum computers, is important? First of all, if you study quantum algorithm, you will see that in all cases, at some point in the algorithm, you generate entanglement. Okay, it's because you are exploiting quantum mechanics. It's the most general feature of quantum information entanglement to have a meaningful quantum process which offers some speed up. So there is entanglement in the device. This is intuition. Now you can be more rigorous and you can actually prove that if a quantum state has a low level of entanglement, it can be efficiently simulated on a classical computer. There are theorems based on numerical methods or tensor networks. If a state has a low level of entanglement, it can be simulated on a classical computer. So there is no point of using a quantum computer in this case. Okay, so in other words, only entangled states are useful for quantum computing. You can also make predictions about how entanglement should be and how large it should be. So you can use entanglement for benchmarks. Okay, so if your device produces this level of entanglement after a certain time, you can compare this to theory prediction, which are analytical. So it's a non-trivial benchmark of quantum computers. And finally, you can also do some physics if you know the level of entanglement. And I will describe this in a minute. So to explain this in more details, I need to explain what I mean by high level of entanglement or low level of entanglement. I need to quantify. So for pure states living in A, B, there is actually one good way to quantify entanglement for any system size is you look at the so-called reduced density matrix in a subsystem, say A, by eliminating the information about B. So writing this trace over here, you get a matrix. And this matrix tells you everything you want to know about subsystem A. And it also tells you everything that you want to know about entanglement between A and B. And for this, you define entanglement measures. So I have row A, you write functions of row A, which are entropies, the same entropies that you see in thermodynamics. Von Neumann entropy, trace row log row, or Rényi entropies with some powers of row. And if you don't have entanglement, the entropies are 0. And as the level of entanglement increases, the quantity will increase to quantify. Rigorously, there are various ways to show that. For instance, you can prove that if you have an entropy of a certain entropy S, you can distillate the corresponding number of Bell pairs. Okay, so it quantify resources, how you can use this entanglement. And it's also related to quantum information. So if you have a certain entropy S, you can bound the number of qubits that you need to explain the statistics of states sampled by this density matrix. It's a bit complicated, but if you're interested, there are some very nice notes from John Preskill, which explains why the entanglement entropy is relevant for all the scenarios of quantum resources and quantum information. So wonderful notes. So the entropy quantifies how much entanglement I have. And this is in particular useful. Now I want to come back to what I said before, to understand the physics of the many-body quantum states which may be created in the quantum computers. In particular, these entanglement entropies, they are calculated routinely in numerical simulation numerical simulation for quantum phases of matter. Okay, so I give you a material with a Hamiltonian, I calculate the ground state, and then I can calculate the entanglement entropies. I can study this quantity. And this quantity displays universal features, so it can be used to recognize a certain quantum phase. One example is the so-called area law. If you have the ground state of a local Hamiltonian, it's expected, it's conjectured that the entanglement entropy will scale as the number of qubits or the number of sites at the boundary. And it's a very different feature compared to what you would expect from a completely structureless quantum state. And then people are trying to see in different many-body models how the entanglement scales as a function of system size. In this plot, it is used actually to detect a quantum phase transition between two phases, localized phase, ergodic phase. And the critical point is spotted by the entanglement entropy changing behavior. Okay, so in other words, if you can measure the entanglement entropy, you can learn about your quantum system. This was for pure states. So I was showing my qubits A and B, and I was assuming it was completely isolated from the environment. This is of course not true. And so in general, you have to put the environment in your description. Then your quantum computer AB is a mixed state, okay, because I'm tracing the environment. And I have to discuss entanglement for a mixed state. It's much more complicated than what I said before. The definition is that A and B are entangled if and only if I cannot write rho AB as a sum of these product states. That's the definition. But entanglement entropies are still useful in this context. Let me explain why. So I need to discuss a variant of entanglement witnesses. It's an entanglement condition. It means I will be able to detect entanglement based on quantities in a state agnostic way. So I'm not knowing anything about the state. I just have access to some quantities. And the key quantity for me and for my research now is the purity. So I define rho AB as before. Then I take this mathematical operation, trace rho square. It gives me a number. And you can see that this number is 1 if and only if the state was pure. So that's why it's called the purity. And when the state is not pure, it's smaller than 1. I'm telling you about this because if you can calculate the purities, you can show that A and B are entangled. And the condition is if the purity of the subsystem is smaller than the purity of the total system, that implies A and B are entangled. The intuition behind this is typically when A and B are entangled, A and B share correlations. So if you start eliminating the information about B by tracing B and defining rho A, you create a state which is more mixed than the original state. So this is the intuition. Maybe an example helps even more. I give you a Bell state. The purity is 1 because the Bell state is pure. If I start tracing over B, so if I start removing these correlations, I get rho A, which is fully mixed. It's the identity matrix. The purity is 1/2. So based on this entanglement condition, I can prove that A and B are entangled. So purity can be used to detect entanglement. This is very important for me. And This was a bit fast, maybe when I introduced the entanglement entropy. But there is one entanglement entropy, the second Renyi entropy, which is the log of the purity. So if I measure the purity, I also measure the entanglement entropy. I just need to take the log. So this introduction was to tell you that it would be nice if we could measure the purity in an experiment, because we detect entanglement. Detecting is interesting. What is even more interesting is that we can quantify entanglement, and this can be used to benchmark quantum computers, to check that they are pure, that they are entangled. But this can also be used to understand the physics of many-body quantum states in the scenario of quantum simulation. So now I come back to the second part, which is how to measure this purity in an experiment. And for this, I will introduce the randomized measurement toolbox. To do that, I need to explain or recall how a quantum measurement is done in a quantum computer. So in a quantum computer, you have qubits. You realize a circuit, what you want to realize. You realize this with noise, because you have no choice. And then you take the measurement, okay? And the measurement is a von Neumann measurement. You will measure a classical configuration, S, so qubit being 0, 1, with a probability associated with the density matrix, S for S. Okay, so it's not new. And what do you do with this measurement? That's the question. The first thing you can do is you can build expectation values of observables, which are diagonal in the computational basis. So if you measure populations, you have access to populations, correlations between the populations, everything in this basis. Okay, that's my equation 6. Everything is done based on measuring this population S for S, right? Now, observables are nice, but sometimes they are not enough. For instance, the purity is not an observable. Right? It's a nonlinear function of rho. So another thing I can do, I can measure the states in all the possible bases of a system. I have 3 to the n possible bases because I can measure each qubit in 3 bases, x, y, z. If I do that, I have a list of 3 to the power n expectation values, and I can write the density matrix. I have a list of 4 to the n because there are some identities hidden, sorry. I can write then the density matrix rho as a function of all these expectation values, and this is called state tomography. It works, but it's a massive effort, right? You have this exponential number of measurements, and for each measurement, you have to repeat the experiment many times to access the probabilities with a good histogram. So the question we were asking is, can you avoid that? Can we measure the purity without doing tomography? Okay, and can you measure purity without also using ancilla qubits or quantum interference? So just using this structure of measurements. Okay. That's the goal of randomized measurements. And we do that in the following way. So I have my circuit as before, and we are doing something very simple. Before we take the measurements, we apply some single qubit gates, which are U1, U2, these boxes. And the experimentalist can do these gates very efficiently. It's just X, Y, Z rotations. And then you take the measurements. And the subtle point is that I chose these unitaries randomly from a certain matrix ensemble. It means the probabilities that I measure in the end are random. Okay, they are random variables distributed according to U. And we propose to do that because we think that the statistics of this random number are very informative. Okay, so I want to generate a lot of these numbers to understand my quantum state. And the first people who came actually with this idea, it was 10 years ago, Van Eyck and Benacker. And their idea was based on a single Hilbert space. So I will explain this for a single qubit to be more pedagogical. So we are considering this circuit. One qubit, one circuit, one U, one measurement. And then we get a randomized measurement here. And I want to explain that indeed the statistics of this object is related to the purity. And I can show this analytically here. Consider extreme case the state is pure. Then the purity is 1. And then you can show that this probability here, if I plug in some example pure state like 0, 0, I get that the probabilities is just a matrix element, SU0. It's just putting this into that. So if I take a random U, P of U is also random because it's just a matrix element. So I will see that this number will fluctuate as a function of U. So pure states fluctuate with randomized measurements. And I can take a second example, which is the other extreme case. The state is fully mixed, okay, so completely affected by decoherence. The purity will be 1/2, and the density matrix will be the identity matrix. If I plug the identity matrix rho, into the expression of P, I get P equal 1/2 because I put the identity matrix. So mixed states do not fluctuate. And that's the insight from Van Eyck and Benacker. The purity is revealed by how the randomized measurement fluctuates as a function of U. And they proved it analytically. So in our case, we were very much inspired by this, and we tried to generalize this to many qubit rotations. So it turns out you can repeat what Van Eyck and Benacker did for this case. We have many qubits and many unitaries. And the formula is a little bit more complicated, and I now want to jump to the experiments. But the formula exists. Okay, so on the left-hand side, you have what you want to measure. And on the right-hand side, you have what you can measure, the probabilities. Okay, and we have this simple mapping, simple equation, which gives you what you want to measure as a function of what you can measure. And first, we were very happy with this expression. And it turns out it's useful. Okay, so the fact that this expression is simple means also it's robust. So there is no fitting, there is no numerical inversion, which could be unstable. You can also unbias the statistical terms one by one. And you can also find that typically the number of measurements that you need is of the order 2 to the n. So it's still exponential in system size, but it's exponentially smaller compared to what you need with tomography. In practice, it means now you can measure a purity up to 20, 25 qubits, which is comparable to current experiments. So I wanted to show a step-by-step example for the first experiment. And it's about a trapped ion quantum computer, a quantum simulator, actually. And it's very different from a superconducting qubit quantum computer, but it achieves the same level of fidelity at the moment, I would say. So what is this? So you have an ion trap. This was in Innsbruck. In this ion trap, you have a couple of ions, which are trapped with laser beams separated by a few microns. And because this distance is quite large compared to the laser wavelength, you can shine lasers and address electronic levels of these ions and make qubits out of this. So you can change the state from one level to another one. you can read out, so measure using a different line. So you have a small quantum computer. And you can also make entangling gates using the lasers. So what these guys did in Innsbruck, that they prepared a 10 qubit quantum state. They evolved with entangling operations, and then they did the randomized measurement sequence. The goal was, can we check that there is entanglement and how much? And here I show you the experimental results. So you have the purity measured as a function of the size of the subsystem. So I'm trying to see if qubit 1 is entangled with the rest, qubit 1 and 2 are entangled with the rest, and so on. That's the x-axis. And I'm plotting different colors for different times of evolution with the system. So time 0, the state is not so much entangled. It's supposed not to be entangled. And you can see that the purity is order 1 for any system size. It means, to a good approximation, I have indeed a pure product state. And what happens at later times is that this curve decay. And it's because if I take the log of this curve, I get the entropy. Then you see that the entropy increases as a function of time. It's a sign of entanglement growth measured in this system. This is for subsystems. If you look at the entire system, so I equal 10, then you see that the purity stays constant. This is also a good sign. It means the dynamics is unitary to a good approximation. So this was a nice result because we could check for a very large Hilbert space of dimension 2 to the power 10, so 1024, that we had a good many-body quantum state generating entanglement in a quasi-pure state scenario. So what can you do with this in our context? Let me illustrate this with two last examples. Now in quantum computing, this was the Google chip. And I guess Pedram Roshan explained this. It's a 2D chip, so you can prepare states which have interesting properties in terms of quantum error correction or topology. So now you can engineer very complicated many-body quantum states. And what they did in this publication is that they prepare a toric code. The toric code is a state which is important for quantum error correction, but also for quantum science in general, because it has topological order. So it's something very interesting from the physics side. And the question is, I create topological order. How can I prove that there is topological order? And the only reasonable proof that I know is based on the entanglement entropy. So you have to calculate a complicated sum of entanglement entropies. If you have topological order, this complicated sum should be equal to -1. So experimentalist has a mission. He has to measure these complicated entropies to check topological order. And in this case, they used the protocol that I showed you. And they could measure this topological entanglement entropy of -1. And yeah, so this was another illustration of how this can be used. So you can check entanglement growth, but you can also check in which quantum phase you're sitting in this case, topological order. And now many different experiments use this measurement of the entanglement entropy to check this or that. So I guess maybe I have 1 minute to finish. I explained the purity because I care about this, and I think it's interesting, but it's important to emphasize that now the measurement possibilities of quantum computers are go beyond the purity, and you can measure many things, and sometimes they are even unexpected. And I would like to give a last example in this context about verification. Okay, so I prepare a quantum state in a quantum computer. I want to verify that it's the one I wanted. Something you can do, if you cannot calculate the dynamics with a classical computer, you can compare two quantum computers. So you have quantum computer 1, you trust it. It was established a long time ago. It was benchmarked before. And now you have quantum computer 2, just arrived, and you want to check that they produce the same quantum state. Yeah, they are able to prepare the same quantum state. So you need to measure overlaps between two quantum computers. And it sounds very difficult because the two quantum computers are not in the same place. They can be in two different continents. There is a way to do that, actually. It's using the same tricks as before. So on a quantum computer 1, I generate randomized measurements, P of S. And on quantum computer 2, I generate another list of randomized measurements, and I will compare these two based on our formulas. And you can actually show that the overlap is a function of what you can measure. So you can reconstruct a quantum overlap by correlating measurements which occurred in two different places. And it's because this is classical information on the right-hand side. So it's a bit peculiar, right? But it was done very recently, and people have tried to compare different devices. So you always have this interesting battle between superconducting qubits and trapped ions. So here it was a group of trapped ions which compared their IonQ devices, compared it to IBM. And they measured some numbers. I don't want to comment too much on this because it was one single experiment and all the technologies are improving and so on. But they could measure that they obtain reasonable fidelities and the devices produce more or less the same states. They also saw some errors. So the fidelity was not 1, obviously. And now they can build on this measurement to improve the device even more. Okay, so to conclude, it's interesting to measure entanglement, and I have presented one approach to do that. I focused on the purities, but over the last year, people have shown that you can measure many things. Some quantities were measured for the first time using these techniques. For example, quantities associated with the negativity or symmetry resolved Rényi entropies, quantities like this. We have also worked on improving the data analysis because in the end, we are treating classical data, this random number P of S. They are classical numbers, and we are trying to understand how we can extract the best estimation from these numbers. And this enters the field of machine learning, importance sampling, all these kind of classical tools. And if you want to know more, we just wrote a review about this with the Caltech team and the Innsbruck team. And thank you for your attention.
We have a question here, Kigali, and then after that, we'll take the questions in the chat.
So you mentioned that the number or the complexity scales like 2 to the n with your with this approach. So can you show if this is the optimal procedure, or in principle there are ways that less continue? I don't know.
Yeah. It seems it's the optimal you can do based on this protocol. So measuring the quantum system as I described. If you allow for more operations, you can do better. So for instance, if you have 2 copies of your quantum state, you can do a Bell measurements and have the purity in a better way. But of course, the resources are not the same. So this is one answer. You can try to change the protocol. The second answer is you can try also to put assumptions. So if you know your state has a certain structure, for instance, it's a matrix product state, then you can better also estimate these quantities, but it's at this time at the expense of making assumptions. So the formula I showed you was assumption free. It will always give you a purity. But it's a good question.
Thank you very much. We have 3 questions in the chat now. There's a question from Lakshmi Prasad. Why purity is considered as a measure of entanglement? I mean, is there any advantage over other measures since there are other measures of entanglement as well?
So the purity is the easiest quantity to measure entanglement. It's not the only one. For instance, there is the von Neumann entanglement entropy, which satisfy more properties on the quantum information side. The problem is that it's more difficult to measure. And we are also trying to see is there a trade-off? Like the quantities that are easier to measure are not always the most informative. And at the moment, we don't know the answer. So what exactly you should measure in order to check this or that property. For instance, in quantum simulation, we know that the Renyi entropy, the purity, and the von Neumann entropy have the same properties, but we know that the purity, second Renyi entropy, suffer more from finite size effects. So it displays less clean signatures of the quantum phases. So sometimes you may want to measure other measures.
Okay, thank you. Dr. Isaac Nape has a similar question. Is purity still a good measure of entanglement since pure and separable states can also have a high purity? Or is there a condition that I missed that makes it a valid entanglement monotone that is sensitive to separability in both the context of pure and mixed states?
That's an excellent question. Yeah, I wanted to put some slides about it.
Okay.
Purity is a good measure for entanglement if the state is pure, and only if the state is pure. If the state is mixed, you need other measures. And it was in the last slide I mentioned. If the state is mixed, one good measure, for instance, is the negativity. And it's more difficult to construct, but you can also construct estimator for this and measure this. And in this case, it will work even if the state is highly mixed.
Okay, thank you. Abdullah Tunsi has a question in the chat. Could we use Bell inequalities to detect entanglement?
Yes. Yes, you can, but Bell inequalities are simple for 2 qubits, two entities. And if you have n qubits, it's not easy to derive a Bell inequality which will detect entanglement for your quantum state. So you can do that, and there are actually numerical programs to derive Bell inequalities, but it's non-trivial. The power of detection of a Bell inequality depends very much on the quantum state that you are probing. So you may detect entanglement, but you may also not be able to detect entanglement. And this other approach that I'm using, based on entropies, the idea is to be more state agnostic. So I don't know anything about the state. I just try to measure purity, and then I can make a statement.
Thank you. Let's take one more question. Is negativity easier to measure compared to purity? This is a question from Lakshmi. Negativity easier to measure
It is similar scalings. We observed this factor of 2 to the n, but it was not exactly for the negativity. It was for an entanglement condition which is based on the negativity. I can send the paper if you ask by email.
Yeah, you can put it in the chat.
I'm going to put it in the chat. Yeah. So this measurement was done 2 years ago for the negativity related quantity.
So thank you very much. So let's thank
Thank
Professor Benoit once again.
Thank you.